Hi, I am Swapnil Patil with another interesting and learning episode of B.Pharm on the important unit of crystallization 2. Crystallization, those units are very important in section of Physical Pharmaceutics 3rd semester. The content expert of this lecture is Dr. Kavita Singh. Let's start our episode while taking a look at what we are going to learn today. Module 1 is for the introduction. Module 2 is having scenario of crystallizers working on supersaturation by cooling alone. Module 3 contains crystallizers working on supersaturation by evaporation of solvent. While in Module 4 we refer crystallizers working on supersaturation by adiabatic cooling. In Module 5, that is the last module in which we deal prevention of crystal caking. Let's take one by one modules. Module 1, that is introduction. We have already learned in the first part of this topic, that is crystallization 1, that crystallization is chemical solid liquid separation technique in which mass transfer of solute from the liquid solution to a pure solid crystalline phase occurs. In chemical or pharmaceutical engineering, crystallization occurs in a crystallizer. In this chapter, we shall discuss the types of crystallizers available along with their working advantages and disadvantages. Let's look towards crystallization equipment. Those are classified by the methods by which supersaturation is brought about in the process as given below. That is, first class supersaturation by cooling alone, in which A, that is the batch processes, in which types further divided like tank crystallizers, second type agitated batch crystallizers. While in a B, that is continuous processes, there are two types, that is Swenson-Walker crystallizer and other one. While in second class, that is supersaturation by evaporation crystallizer, that is crystal evaporator, we will discuss those. In third type, supersaturation by adiabatic cooling, in which a vacuum crystallizers. In fourth type, that is supersaturation by salting out, we will discuss those crystallizers in further discussion with types of crystallizers in further module. Classification methods, we discuss classification of crystallizers. Classification of crystallizers are divided into the four methods. Method 1, that is supersaturation by cooling alone as on your screen. Method 2, that is supersaturation by evaporation of the solvent, that is crystal crystallizer. Method 3, that is supersaturation by adiabatic evaporation, that is cooling plus evaporation. Vacuum crystallizers, that is having further dividation, that is without external classifying seed bed with classifying seed bed. While method 4, that is supersaturation by salting out method. And in method 1, there are further sub points, that is batch crystallizer, continuous crystallizer. In a batch crystallizer, further subdivided into the tank crystallizer and agitated batch crystallizer, while continuous crystallizers are as like on your screen, Swanson-Walker crystallizer and others. This is all about classification of crystallizers. Here, method 1 is suitable when solubility of compound follows steep solubility curve indicating a rapid decrease in solubility with a decrease in temperature. Solution are concentrated in a separate evaporator and then fed to the crystallizer. These crystallizers functioning on cooling technique are most commonly utilized since majority of substances exhibit this kind of steep solubility curve. Now, method 2 is preferred for compounds which have intermediate solubility profile. Neither they are flat nor they are sharp. Also, such compounds exhibit very low yield of solid by cooling method. Example, sodium chloride. In method 3 is of utmost significance for industrial scale crystallization. If a heated saturated solution is introduced into the crystallizer in which sufficient vacuum is maintained, in which the total pressure lower than vapor pressure of the solution, at that temperature the solution will flash and cooled by adiabatic evaporation. resulting in supersaturation and subsequent crystallization. This method increases the yield of crystals. The method 4 deals with concept of addition of substances which reduces the solubility of the compound to be crystallized, resulting in supersaturation causing crystallization, also called as salting method. It is not a preferred method at the industrial scale. These are all about the methods of crystallization. Now friends, we will discuss module 2, that is crystallizers working on supersaturation by cooling alone. These crystallizers functions by utilizing the simple mechanism of cooling. They are categorized into batch crystallizer and continuous crystallizer. Most commonly used batch crystallizers working on supersaturation by cooling alone are tank crystallizers and agitated batch crystallizers. In which tank crystallizer, this is the simplest and oldest method of crystallization. The instrument used is without any moving part. Crystallization is allowed to happen at its natural rate and the method produces very large crystals, interlocked and entrapped with mother liquor. Briefly, the procedure involves preparation of hot nearly saturated solution followed by running these solutions in an open rectangular tank. The solution is allowed to cool, causing a deposition of crystals. The tanks are cooled sufficiently several days and the remaining mother liquor is drained off and crystals are separated manually. Let's look limitations of tank crystallizers, which includes in this method no attempt is made to seed the tanks, to provide agitation or to accelerated or controlled crystallization. Crystal growth is slow with large crystal size which may get interlocked. It requires a big floor space, amount of material required is large and its labor intensive method. Occlusion of mother liquor may introduces impurities. The second type, that is agitated batch crystallizer. It consists of a cylindrical container as in your screen with a conical bottom having propeller picks centrally which rotates on its own axis with the help of motor for conducting heat. Pipes and or coils are attracted to the unit. It works on principle of supersaturation by reducing the temperature. Solution is placed in crystallizer and cold water is circulated through the cooling coils. The solution is agitated by propellers on the central shaft and this agitation performs two functions. First, that is increase a rate of heat transfer and keeps temperature of solution more nearly uniform. Second, by keeping the fine crystals in suspension, it gives them an opportunity to grow uniformly instead of forming large crystals or aggregates. Crystals are collected from the bottom of equipment by the suitable method and processed further for the separation of mother liquor. What are the advantages associated with this method? Crystals are formed are uniform and fine. While disadvantages, it is a batch or discontinuous equipment. Rapid crystal growth at the surface by cooling coils is observed which decreases the rate of heat transfer. Third type is a Swenson-Walker crystallizer. In Swenson-Walker crystallizer is an example of continuous crystallizer working on principle of cooling alone. It consists of a long open trough with semi-cylindrical bottom and external water jacket as on your screen. It has a slow speed, long pitch and spiral agitator, that is scraper, running very close to the bottom of trough at 7 rpm. It has 10 feet long built-in units and the number of units may be joined to increase the capacity. The maximum length usually driven from the one shaft is 10 feet long. For still higher capacity, larger units may be arranged one above the other such that solution cascades from one unit to another. Hot concentrated solution is fed at left side of the crystallizer and cooling water enters through the jackets in the other end. The spiral scraper rotates on the own axis. Its purpose is not only for the agitation of crystals or conveying of crystals, but to prevent accumulation of crystals on cooling surface and lift the crystals that have been formed. In this manner, the crystals grow while they are freely suspended in the liquid, and usually fairly perfect crystals of uniform size which are free from inclusion or aggregates are formed. If necessary, size of crystals may be controlled by injecting extra amount of cooling water into the selected sections. Crystals and mother liquor are made to overflow through a gate to a drain table or box. Mother liquor is returned to the process and wet crystals are centrifuged. Screw conveyor may also lift the crystals. Advantages of this method: large saving in floor space, material in process and labor. Crystals formed are uniform and free from inclusions or aggregations. This is the continuous process. While some disadvantages are also associated with this process, that is, scraper may break the crystals to the little extent. Now friends, let's begin with the module 3, that is crystallizers working on supersaturation by evaporation of solvent, in which crystallizer. In this crystallizer, concentration of liquid and crystallization process are carried out in different chambers. Concentration, that is supersaturation, is induced by evaporation of hot solvent with the help of vacuum pump. In the crystallization chamber, the solution and crystals are maintained at fluidized state. Crystals of desired size and settle down by the gravity, and fine crystals along with supersaturated solution is recirculated for further crystallization. It has two chambers: vapor head flashing chamber, which has a long tube connected to the pump, and crystallizing chamber for crystal growth. Vapor heated consists of a long tube which extends to the bottom of crystallizing chamber, whereas other end of the connected to condenser and vacuum pump. A pump is provided which allows the feed to enter vapor head. On its way to the vapor head, a heater is provided. A solution is pumped which passes through the heater, and hot solution enters the vapor head. Due to the reduced pressure, hot solution undergoes flashing, which results in formation of solvent vapor and supersaturation solution. Vapor is removed by suction pump. Supersaturated solution passes through long tube below, and the operation is controlled such that crystals do not form in vapor head, but they get formed in crystallizing chamber. Crystallizing chamber consisting of bed of crystals suspended in an upward flowing stream of liquid, while supersaturated liquid flows through bed of crystals which are maintained in the fluidized zone. Uniform temperature is attained and there is a continuous gradation of crystals in the chamber, while coarse crystals settled at the bottom, while fine crystals remain above the coarser ones. Very fine crystals overflow through the liquid and enters into the recirculating systems, which combine with the fresh feed. Coarse crystals are removed from the time to time. It's having the advantages. It is a continuous method preferred when large quantities of crystals of controlled size are required, and these crystallizers are available in very large sizes, that is 4.5 meter diameter and 6 meter height. It is used for the crystallization of sodium chloride and magnesium sulfate. While it's having the disadvantages, it is the expensive method. Now friends, let's move towards module 4, that is crystallizers working on supersaturation by adiabatic cooling, in which we deal vacuum crystallizer. Vacuum crystallizer operates on principle of supersaturation by adiabatic evaporation cooling. It is made up of cylindrical body with the conical bottom as on your screen. A condenser is attached to the crystallizer with the vacuum pump in between, and the bottom of the crystallizer is attached to the discharge pipe, whereas internal body of the crystallizer is lined with acid resistant material such as lead or rubber. The propellers are placed above discharge pipe to prevent short circuit of feed. The crystallizer functions by creating high vacuum using a vacuum pump. The vacuum created must correspond to the boiling point of the solution but should be lower than feed temperature. Hot or warm saturated solution is fed into the crystallizer at a convenient point. Vacuum is maintained such that solution will flash on entering. This results in evaporation of solvent, thereby causing cooling of solution. In this crystallizer, adiabatic cooling causes supersaturation and crystallization. In this method, evaporation of solvent enhances yield. Flashing leads to the ebullition, which keeps crystals in suspension until they become large enough to fall into the discharge pipe. Propellers are used to mix the contents thoroughly and prevent reaching of contents to the discharge pipe without flashing. The pump helps in collecting the product and subjecting it to the filtration or centrifugation to obtain the crystals, and the filtrate is returned back to the feed. Advantages of it is a simple method without any moving parts. Corrosive materials can be used in vacuum crystallizers. It can be constructed as large size as desired. It can be operated batch-wise or continuously. It is suitable for thermolabile substances due to low temperature conditions. While it is having the disadvantages, it is a relatively an expensive method. Second type, that is a circulating magma crystallizer. Circulating magma crystallizer, it is a slight modification of vacuum crystallizer. It consists of a main body, feed and special pump called screw pump used for moving large volumes under the low heads. It has U-bend casing in a pipe, and the pump impeller consists of several turns of deep screw thread made by attaching helical fins to the pump shaft. The pump circulates crystals suspended in solution called magma out of body through the header and the back to the body. Impellers serve to mix feed thoroughly with the circulating magma. If feed is hot enough to cause a desired amount of flashing, no heat will be needed in the heater. In this case, heater is used to heat the feed if not hot enough for flashing. Initially, a small crystals are formed and are kept in a suspension in circulating liquid. They eventually grow in size. Large crystal settles at the bottom and removed through discharge. By introducing a wash stream of saturated solution, the velocity of rising stream can be made sufficient to wash out column fine undesired crystals and return them to main circulation. Baffle is provided to give a stream of saturated solution free from crystals. Such as a process is called elutriation. Suspension of crystals of desired size is removed by pump. Let's look towards crystallization working on supersaturation by salting out method. It is not a frequently used method. It involves a deliberate introduction of foreign substance to decrease the solubility of crystals. By addition of third substance, solubility of substance in solution reduces such an extent that the desired solute crystallizes out. Indirect application of this technique is found in evaporation of electrolytic caustic solution and in glycerin soap solutions. Due to the presence of caustic soda and glycerin in high concentration, the solubility of solute decreases. As the concentration of very soluble component increases, the solubility of less soluble component decreases to the point where it crystallizes out of the solution. Now friends, let's move towards the module 5, caking of crystals. While handling the crystalline products, a major difficulty is encountered due to their tendency to cake or bind together. and this is particularly a problematic in bulk storage and in large containers, but it is the most serious in small packages. Thus, caking can be defined as the process of formation of lumps or cake when crystals are improperly stored. The extent of caking may vary from formation of loose aggregates that fall apart between the fingers to solid lumps that have to be crushed with the considerable force. As the consumer demand is to have a free-flowing product, prevention of caking is a severe setback for manufacturer. After the caking, the flow properties of the powder are affected negatively, and the powder will not flow uniformly from the hopper into the die cavity of the tablet punch machine. In capsule filling will not be uniform, filling of punches will not be uniform. If crystal of soluble salt is in contact with the air that contains a less water than would be in equilibrium with the saturated solution of salt, and the crystal must stay dry, since if the crystals were to be surrounded with the film of its solution, that solution necessarily evaporates. On the other hand, if the crystal is brought into the contact with the air containing more moisture than would be in equilibrium with the saturated solution, then the crystal will become damp, and in time crystal powders can absorb the moisture when the humidity of the air is above the critical humidity. Below this critical humidity, the crystals do not absorb the moisture, while above the critical humidity, the crystal absorbs the moisture and forms a saturated solution on the surface of crystals. When the temperature of the crystal is lowered due to some reason, or the water is evaporated from the surface, the extra solute crystallizes out and thus may form a solid bridges in between two adjacent crystals called crystal bridges. Thus, the crystal particles will join together to form hard aggregate, and these aggregates or lumps are called caking. The condition of maximum critical humidity is often met by removing impurities such as calcium chloride in common salt, since it often happens that the impurities have lower critical humidity than the product desired. Factors affecting caking. 1. Size of crystals. Smaller crystals have a greater tendency of caking than larger crystals because powder of smaller crystals have less void, so greater number of contact points. More the number of contact points, greater the number of crystal bridges will be formed. Second, that is shape of the crystals. Spherical shape possesses the least possible points of contacts than any other form. Hence, the distorted crystals tends to more caking than spherical particles. While third, that is humidity. The higher the humidity of the atmosphere to which crystals are exposed, more will be the rate of caking. Fourth factor, that is time of exposure to the moisture. The higher the time of exposure, the more will be the caking, provided that the atmosphere has humidity more than the critical humidity. Fifth factor, that is impurities in the crystals. The crystals may be coated with the impurities from the mother liquor, and this may increase the value of critical humidity. For example, MgCl2 and CaCl2 alters the critical humidity of sodium chloride crystals. Sixth, that is melting point of crystals. If the melting point of crystals are near room temperature, then at slightly high temperature they will melt, and at low temperature they will fuse to form crystals and thus increases caking. Seventh factor, that is temperature fluctuations. When the temperature is increased, solubility of crystal increases. Subsequent decrease of temperature will produces a supersaturated solution from which crystals will be precipitated. So the fluctuations of temperature produces crystals rapidly. In summary, following precautions must be taken to prevent caking of crystals. That is, crystals must be more spherical in shape with least points of contact. Crystals must be larger in size with more voids, must be of a narrow size distribution, that is, must be more uniform in size. Crystals are packed and stored in atmosphere where the humidity is less than critical humidity. Crystals may be coated with the powdery inert material to prevent absorption of moisture, like sodium chloride is coated with magnesia or tricalcium phosphate. Friends, this is all about crystallization. Now let's move towards the conclusion. Crystallization equipments are classified by the methods by which supersaturation is brought about in the process, such as supersaturation by cooling alone, by evaporation, by adiabatic cooling, or by salting out. Considering the basic mechanisms involved, the major industrial crystallizers can be listed as tank crystallizers, agitator batch crystallizers, Swenson-Walker crystallizers, crystal evaporators, and vacuum crystallizers, etc. This module also deals with the phenomenon of crystal kicking, its mechanism, and its prevention. While handling the crystalline products, a major difficulty is encountered due to the tendency to cake or bind together. The extent of caking may vary from formation of loose aggregates that fall apart between the fingers to the solid lumps that have to be crushed with considerable force. After the caking, the powder does not flow uniformly from the hopper into the die cavity of tablet punch machine. Filling of capsules as well as punches is non-uniform. Caking can be prevented by use of spherical crystals, which are larger in size with more voids with a narrow size distribution. Crystals must be packed and stored in atmosphere where the humidity is less than critical humidity. Also, crystals may be coated with a powdery inert material to prevent the absorption of moisture, like sodium chloride is coated with magnesia or tricalcium phosphate. With all these information, here we came to the conclusion. Do keep in mind what we discussed today. It's time for you to do self-study. This is Swapnil signing off. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website for MCQ, quizzes, LORs. You may log on to our website www.cec.nic.in. Till then, keep studying. Goodbye.